Hello everyone. In today's video, I'm going to continue the 5G non-standalone training. Today's video is going to cover the part related to 5G downlink transmit power, consideration and calculation, and also other factors. Actually, the 5G power in general is calculation, especially is more simpler compared to the 4G. 4G was kind of complicated. However, the 5G is more easy. And just to highlight, this power calculation or the downlink transmit power calculation is not only limited to 5G standalone, it's also applicable to 5G standalone. So let's move forward and see what we have today. Okay, this is actually what we are going to cover in today's video. As you can see, the points in the middle, that first we will go through the meaning of what it means by EIRP, effective isotropic radiated power, just to recap the knowledge about it. This is usually you require to understand this because usually we hear like this. You are working for a vendor or working for an operator, that sometimes the national regulator, there is a national regulatory requirements which require or requesting or asking the operator to set a maximum EIRP power, which is actually like kind of a regulation. Each country might have a different regulation at this particular part. So we will discuss about what it means and how it can be calculated and so on. And this is a second part that is about what is the EPRE, which is energy per resource element. And this is actually usually like it's something called our reference power. This will be calculated, like defined whenever we go for the third part, which is about how to calculate in general the reference power and also the power for the other channels, which is SSP and so on. Then in between, we'll be discussing about how to check in general the configured power, for example, for SSP from the logs or from the UE logs or from layer 3 messages. And then we'll be ending about like whenever you do SSP power posting, like for example, sometimes you need to increase the SSP power. So to what would be the impact on the throughput and the coverage in general for SSP coverage and throughput, and why this impact, for example, if you're degrading the throughput or improving the throughput, why this impact is happening. So this is all we'll understand. So let's move forward and see what we have. So what it means by EIRP, effective isotropic radiated power. Actually, it's the similar, it's a very easy one. But first, let me to highlight one thing, which I was already highlighted in the previous slide, that sometimes the national regulators may specify a maximum permitted total EIRP per megahertz. For example, they tell you I need, let's say, 20 watt per megahertz or 2 watt per megahertz or whatever, like depend on them. So you need to follow that. So to follow the regulation requirement, you need to understand how the power is being calculated, which is called effective isotropic radiated power. And as you can see in the right figure, it's very simple. Like you have the transmitter and you have sometimes you have a cable losses, for example, the passive antenna, and you know the antenna gain, right? So you combine all of that. So for example, it's easily equal effective isotropic radiated power is equivalent to the output power, okay, plus for which is TX power minus the cable losses plus the antenna gain. So in this case, you will understand, like you can calculate what is the requirement and what is the maximum EIRP and what is the requirement from the government or for the regulator. So in this case, you can accommodate for whatever you have. And here I have give some examples, and this is quoted from 5G and RM Bullet spoke. Some examples about the passive antenna and the active antenna as well. But the main takeaway from here, which I would like you to consider, like whenever you do the calculation, that still, for example, in TD, especially in the TDD system, the current configured like TDD pattern or TDD duty cycles, this is also the tropic power. For example, if you have 60% of the slots being allocated for downlink, this means downlink transmit power will be reduced by around 2.2 dB when you apply this 60% factor within 10 log, so it will be reduced by around 2.2 dB. This is the main key takeaway here whenever you consider on top of the formula which we already highlighted here in the top right. And for more details, maybe you can refer for this link, which is a good one, I believe. It's having kind of details, and also there is many videos about that, but in short, it's very easy one, as you can see here. So let's move forward and see what we have about the power calculation for 5G. Before jumping into the 5G power calculation, I would like just to address some few important points. First of all, as I mentioned, the power design in 5G is very simple compared to 4G. 4G was kind of more complicated, like considering something called BAPP, many other stuff. Like, but in 5G, it's more easy compared to 4G. And actually, the main consideration you would like, and this is your main inputs. First of all, you need to understand what is your hardware capability. For example, you have AS or AU, which is the active antenna. you know what is the maximum power. For example, you can see here the maximum power assuming as 320 watt, 160 watt. So you understand what is the maximum power, then you give your requirement. For example, I would like to have a 200 watt based on, again, the IRP or the national regulation and whatever, and based on your also optimization. So first you need to understand what's your maximum power of the hardware capability. You need to check that because you cannot cross this value. And also the number of branches or TXRX supported as well. You need to understand that part. And ending by the bandwidth again, because whatever power configured per bandwidth, it will vary. For example, 20 megahertz moving from 20 megahertz to 40 megahertz. In this case, if you would like to maintain the same coverage or same power, so same coverage you would like, in this case, if you move from 20 to 40 megahertz, so in this case, you need to double the power. So you need to understand that because at the end, you cannot cross the hardware capability. Then once you define, have these inputs, you can calculate something called set reference power. And this is like a reference power being used to be used by the other channels whenever you are going to calculate the coverage of the channels or signals, which I will give examples about it. For example, I would like to know what is my SSP coverage. So usually it will be directly using your calculated cell reference power, assuming there is no offset. So all of that is offsets, compared to the cell reference power. And there is also relations between the different channels and different signals. So whenever you increase for one of the channels, the other one might remain the same, or even sometimes reduce, or might even be muted. So we'll discuss all of that in the next slides, but just keep into mind, this is the key major factors, which is the maximum hardware capability, bandwidth. This is the major key factors. Then based on that, you can calculate something called cell reference power. Based on cell reference power, you can start now understanding what is your other channel power and so on. So let's move to the next part about the cell reference power calculation. Okay, here we are going to discuss about how to calculate the cell reference power and also how to calculate the equivalent, for example, SSP block power calculation and so on. But all the other channels and signals is an offset from the reference power. And that's why it's called the reference power. You need to know what's your reference power. Then, for example, you can keep the other channels or SSP following the same power, or you can even have more extra offset or even less offset, power boosting or power deboosting. But let me try to explain. This is actually a very simple formula, as you can see here. The cell reference power or reference power, it's equal to maximum transmit power, which is the maximum transmit power, this is your main inputs. This is where you need to configure. You know that, for example, your AAU is supporting 320 watt, so you would like to give 160 watt or 200 watt or whatever. So this is the main value you need to configure. But again, you need to consider when you do the calculation that is not crossing the maximum power. Then here, you need just, in the formula, you need to consider, first of all, what is the resource flux being used in the cell, and you multiply it by 12, which is 12 referred to the number for the number of the subcarrier. And at the end, if you look into the formula, you will understand that this cell reference power calculate the power on each of the subcarriers. As you can see in the bottom figure down here, at the end, this is the power in each subcarriers. So that's why at the end, all the others can be an offset from the cell reference power. For example, we know now, after we calculated that the cell reference power is 18.2, so this is your power for the reference signal. So whenever you need to tune an offset from the others, and I'll explain this one with more visualization next slide. For example, if I increase the SSP power by 3 dB on top of the cell reference power, let's say the cell reference 18.2 or 19 and increase it by 3 dB. In this case, you will need to take from the others or reduce the other cell reference powers, or mute other resource blocks or resource subcarriers within the same location or when you allocate the SSP in order to maintain the same total power. So that's why the power boosting might have some negative impact, especially for the SSP on the other channels like the BDSH. And I will be explaining that in more details in the next slide. Then, just to recall or to summarize, cell reference power equal the maximum transmit power. This is your inputs, and I will go through one Excel now to show how it's being calculated. Then you consider your bandwidth. Then whenever you need to, for example, let's say that you were asked I would like to improve your SSP coverage, like synchronous signal broadcaster channel block power. So in this case, what you need to do, it's very easy. There is other consideration made. You might see it, including number of TX branches, but this is the actual where you are going to see from the field. It's a very easy one. you just have a parameter where you can configure how much power you would like to increase. And this is have some dependencies on the bandwidth and these kind of things. You need to check it with your vendor, but very easy one. Once you calculated the reference power, assuming this one was being calculated as 18 dB, in this case, I would like, for example, to increase my power boosting or SSP power by 3 dB. So I will be adding here. So this one would be 18 plus 3 dB, but at the gain, this will be in consideration of whatever other allocated resources. I will show it as a visualization to understand. And whenever you need to check the power in general, by SSP power from the configuration, this is in 9 standalone. You can find it in a recipe configuration message during the CGNB addition, or in standalone, you will find it directly in the SIP1. And this example, for example, here mentioning under the SIP1 block type 1 here, you can see that there is SS broadcast probe power is 21 dBm or dB, as you can see in this figure. So this is also how you can check it from the UE logs. So let me move forward to try to give more visual explanation, because it will make it more easy to understand. Like, for example, if I have a reference power 18 dB, whenever I increase that part, you might think now I'm crossing my total power or whatever, or I might cross my total power. But this is not the case, because the power will be reused from the other channels or segments within the same location of the SSP. So let's move forward to see what we have. Before moving to the next about the SSP power posting, whatever I have just explained about the set reference power and SSP block calculation, I would like to show you it can be calculated. If you look into this table, which we have it here, I mentioned as 2 steps. Step 1, which is the set reference power calculation, and SSP block, for example. And this is also can be applied for other signals and channels. For example, for CSIRS can be applied as well. But the main, usually what we consider to increase is the SSP offset or SSP power posting. So as I mentioned, first part you need to consider is your current hardware. This should be a fixed value. Assuming that my current hardware is 320 watt, and I will be uploading this sheet, by the way, to the video description. So assuming that you have a 320 watt, so this means equivalent to 55 dBm. This is just a conversion from watt to dBm, because some maybe vendors will find that you need to give the power, configured power as dBm, or others can maybe in watt. So now this is your current hardware capability. Now the inputs which you would like to configure. For example, let's assume you have 2 carriers within the same AU, and this AU supporting total 320 watt. So I would like to give first one as 161. This is my configuration, so I give this as a manual. This is manual configuration. I'm giving this 160 watt, and this is a calculation again that converted to dBm. So in this case, for example, in other vendors, you might give it on dBm, which is B52. And my current bandwidth is assuming as 80 megahertz here. This is also input. You can just change it whenever you need. And this is the number of total resource flux, which we have equivalent to the 80 megahertz. So in this case, the power which being to be used here, it would be around 17.9 dBm or 18 dBm, as you can see, because at the end, this is considering what? The same maximum transmit power, which is, if you click here, it will be that part, which is you configured already as 52. I converted from 160 watt to 52. And this one will be minus 10, right? Log 10, which is a total number of resource blocks multiplied by the number of subcarriers. So you would end by this one. But again, your main configuration would be this one, even in watt or even in dBm. And here I'm just calculating the power per watt per megahertz. For example, I would like to know per each megahertz how much power I have, because at the end, the national regulator, as I mentioned, might ask you to configure a specific power per megahertz. And also, this will make you understand whenever you have 2 carriers within the same site, sometimes you will think, here, this is one configured with 80 watt only. So you think this is having less power, but this is not true, because at the end, both of them having the exact same coverage footprint, because the power distributed over here over 40 megahertz, while here it's over 80 megahertz. So at the end, both of them will almost have the same power, which is power, as you can see, per megahertz is 2 watt here. So this is something also as a note you need to consider, that, for example, if in case now I would like to double, or I need to increase my bandwidth. So if I increase this one to 80 megahertz, I'm expecting this one will go to even half now, because now you can see now what will happen. It went to half value, because at the end, if you would like to maintain the same power, in this case, after increasing the bandwidth, in this case, you need to double your power to 160 Let me just here, I write it here, 160 megahertz. So in this case, you will have 2 watt per megahertz, and your power will be equivalent here. So let me return this one to the previous figure, and this one here to 40 watt as an example. And at the end, here, for example, I'm assuming that one of the carriers is being posted by 3 dB, as you can see. So here the calculation will be this reference power, my reference power, plus 3 dB. And here is being, so this one will be equivalent to 21 dB, while the other one here, it will be equivalent, again, because there is no posting, to it will be around 8 dB. But increasing the SSP power, doesn't mean you are crossing your maximum transmitted power, because again, whatever power being increased, means it's being used or utilized from existing resources. If you read in this comments, I will explain it also in next slides in more visualized way. But for example, if the SSP power is usually transmitted over 20 resource block, okay, and this is like, if you're going to increase, this will borrow the power from the other BDCH resource blocks. So within the SSP block, whatever power being increased, it will be borrowed from the free or the BDCH resource blocks. That's why it's impacting your throughput. And again, because it's not something we are increasing additional, no, it will just utilize the BDCH resource blocks to increase their power. This means we are keeping the same total power. And in general, whenever you need to increase the SSP, there is 2 methods, even through the power posting parameter, which is SSP, for example, offset, or through the maximum power. If you still have, for example, in this example, you have some enough power, because the remaining power here, if you 300, this is the maximum, and you only configured 161, so still you can increase it a little bit. But the good point about increasing the power, it will increase for all the channels, but this one will only increase for the SSP, like as a trade-off for the other available resource for BDCH, and I will show you also how much it will impact. So this is actually how we can calculate, and I will drop again this sheet in the video description. So let's move forward about the SSP block impact on the throughput, also to try to visualize how this kind of power will be borrowed from the BDCH resource blocks and so on. Okay, this slide is just explaining the SSP power posting impact and throughput. I just made some estimated calculation. It's just estimation, like you can say it's something standard. So I will show you also from the Excel, which I just presented a few minutes back, like what will be the variation of the resource blocks expected reduction whenever you increase power posting by 3 dB or 4 dB or whatever. So, but in general, whenever we need to increase the SSP power posting, you know that we are doing that to capture more users from edge users, or also maybe sometimes to improve your setup, right? Especially if you are speaking about non-standalone, to improve your initial access, or even for a standalone. So there is actually might be two drawbacks. No drawbacks. First of all, the gain which we might acquire, you're improving the SSP coverage, we might capture more users, and those users will be edge users. So you're impacting in the throughput for sure as a statistical point of view, because you are capturing more edge users. So this will be reflecting in the OSS KPIs. It might have a reduction because you are getting some edge users with lower throughput compared to your existing average. The second part, which I'm going to explain now, whenever you increase the power, the SSP power offset, not the total transmit power. By power posting, this you need to borrow resources from the existing within the same resource. So for example, if you zoom in here, let me explain. Assume now that this is your SSP, okay, and you would like within this slots of the SSP, and you know that SSP usually transmitted in 4 symbols. So for example here, assuming that you would like to increase it to make a power posting, which means you would like to maintain your total power, but you need to increase the SSP by 3 dB or by 4.2. So in this case, it will need to mute some of the existing resource blocks within the same power here and borrow the power from the resource blocks. For example, here, I'm assuming that from RBG0 to RBG4, this is the SSP block. Assuming that you would like to increase here the power by 3 dB. So in this case, you might mute the other resource blocks 20, 15, this is need a calculation. You will mute all of them to borrow their power, so those will not be used anymore because the power being transferred from here to here. That's why it has an impact on the BDC throughput or the throughput in general. And here I give an example of the calculation. I will show also from the Excel sheet simply about that part as well. So for example, here I'm assuming that what is the impact on BDCH whenever you have resource blocks, whenever you have 100 megahertz. After doing the calculation, I'm assuming that you will have around 0.4% reduction in the resource loss. This can have an impact of 2% or even more or even less, but it's around that value in the throughput in general, if you do the comparison in the drive test. And for example, for 20 megahertz, if you have a less bandwidth in your network, it will even much more higher, because there is the resources, you are even almost utilized more and more, so and like more comparable compared to the existing resource loss. So for example, in this case, it's around 2.4%. So let me quickly go to the Excel sheet to show you also what we have from the Excel sheet about the calculation, to just show you how this can impact different bandwidths and so on. Okay, again, this is just estimated one. It's not something based on any standard, it's just estimated, so it might have some variation from based on your calculation on whatever. So here I'm assuming that this is my inputs here. So I'm assuming that I have the bandwidth of SSP, right, is 20 mega. Sorry, the total bandwidth I'm assuming for the channel bandwidth is 20 mega. I can change that one, but I keep it 20 mega for now. And this is my subcarrier spacing 30, and this is the equivalent for 20 megahertz. We have total 51 resource loss. And we know the SSP is around 20 SSP, right? And based on the number of total resource blocks, the 3GPP defined a particular RBG size. For example, 51 resource blocks, this is equivalent that the RBG size will be equal to 4 resource blocks. So that's why I give here RBG size as 4 resource blocks. So now let's try to modify this value, for example. So here I'm just saying that I'm going to do power posting by 3 dB. I'm going to increase by 3 dB. And here is my bandwidth, is 20 megahertz. So in this case, after the calculation, after calculated how many resource blocks would be muted, because I need to mute some of the BDSH resources, as I mentioned. So it will be around 20 resource blocks. And at the end, this is at the end of the calculation, it's just giving you the reduction of the resources in general, it will be around 1.3%. And increase, for example, it will be less because you are increasing your bandwidth. And also, if you increase the power more, this means you will mute more resource blocks of the BDCH. So even this value will increase. So you can see it now become around 1%. Again, this is estimated, but this will just give you some indication about what will happen when you increase the power posting. So in a nutshell, whenever you increase the SSP power posting, this will have a negative impact in throughput because of two things. First, for extending the coverage, capturing more edge users. Secondly, because you are reducing the available resources for the BDCH within the same location of the SSP whenever it's being transmitted. And the idea to maintain the total power, that's why it's formed from the other channel. So now let's move to the next one. Okay, I quoted this picture from 5G and R in bullets. And again, this is similar to whatever I was discussing about the SSP now. It's just giving you that whenever you increase the power on one of the channels, it should borrow from the other one in order to maintain your total power. So this means that you should be very careful when you optimize. For example, in general, we have only mostly on the most of the vendor, only 3 parameters. For example, here I'm highlighting BTRS. We have BDCH, we have BSS, we have others like CSIRS or whatever. But in general, based on my experience, but this is, you might confirm it in the comments as well, that there is SSP power posting, and also there is a parameter particularly called power control offset, and this is related to the CSIRS. I will explain it also in next slides. Also, we have another concept about between the DMRS and BDCH. For example, whenever you you can increase the DMRS power or reduce it post DMRS power through something called BDC multiplexing. But it's not through an offset. It's through that deciding that the BDCH within the DMRS is going to be muted or be going to be used. I will explain that part, and I already explained it in the previous video as well. So if you look into this figure, it's just telling you that usually the second SSS is the main reference for the downlink transmit point. Just to summarize it here, okay? Here, the most important part, because this it will kind of looks complicated, because, for example, I never see this part in any network. But anyway, I'm going to discuss or explain whatever I understand from the practical point of view. So again, SSP power posting, it will mute anything related to BDCH. And also there is another relation between the CSRS and the SSS through this parameter, which will be explained in the next slide as well. And I will show you how we can give it from the layer 3 as well. So this is like power control offset, for example. This is saying that whenever you increase or reduce the CSRS power, this might have an impact on the SSS, which is whenever you increase or reduce the CSRS power through this particular parameter. Also, there is, this power control offset SSS, which is between the CSRS and SSS. And also there is a reference between the CSIRS power and the BDCH, which is controlled by this parameter called power control offset. And this is one of the common parameters. The other one is not really, you'll not even find it sometimes from the layer 3. So the main two is this power control offset and the SSP power block as well. So for example, here it's saying that whenever you increase the CSRS, it might borrow from the BDCH channel. And this is the same concept. Increase the power of the CSRS, so you will have a negative impact on the traffic channels and CQI and this kind of thing. So it might have sometimes a negative impact on the throughput. But it's based on the scenarios, not necessarily to have you might have a gain in throughput as well, because you will be improving the channel modulation. So you might get a better beamforming weight and so on. So it depends on the scenario. So you should be very careful. And between the DMRS and BDCH, this is like whenever you would like to do power boosting or increasing the BDCH DMRS power, or even keep it the same. This is like not on offset. It's like something like a feature or parameters being controlled usually by the vendors. And there is also a relation between the BDCH and BTRS, but I never seen that part as from the practical point of view, and also between BDCH and the SSS. But again, I never see this part as well. And this one is stated by 3GPP, because you know that the BSSS in general is, if you look, I don't have the picture, but if you remember in the SSP block, it's being in the left side and it's having a lot of free resources. So you can even post the BSSS power by around 3 dB more than SSS, because it's already have a free resource. So it can utilize that part over here. But also I never see any configuration for that part. So just to recap here, the main parameters which can be tuned, the CSIRS relevant and equivalent to BDCH, and also BDCH equivalent to DMRS. And let me show an example for the BDCH to BDCH, and I will explain the parameter which being used here in the next slide as well. And this one is just showing the one which is I was speaking about, the relation between the DMRS and BDCH. As we mentioned, in general, the DMRS is always associated with the BDCH or with BDCH, depend on, as you know, each channel have a DMRS, limitation of the signal. So here speaking about downlink only, that's why I'm aligning the BDCH. So for example, here in this left figure, I'm assuming that the BDCH multiplexed, which means that the DMRS being transmitted, but the BDCH is not being used. So in this case, the DMRS power will be boosted by 3 dB, or it will be even increased or double, because it can utilize the free resources, and this can improve even your DMRS performance, demodulation reference signal, but in the same time, it will impact your maximum throughput, because whatever free resources here is not anymore utilized for BDCH resources. So in case you would like to use a multiplexing, here this is a typo, this is without multiplexing. In case you would do multiplexing. Multiplexing means now you would like to use the free resources, which was unused here, to the BDCH. So in this case, the power need to be distributed across the BDCH and the DMRS. So you will like a trade-off. Your power will not be boosted anymore. So it will have around 0 dB boosting. So in this case, your DMRS coverage will be impacted, but your maximum speed will be improved. So this is just an example for whatever I was discussing in the previous slide. Now let's move to the last slide, which is just a quick one about the parameter related to CSRS. Okay, here also I put these parameters from 3GPP, and also it's available in 5G NR and bullet spoke. Here you can see that there is 3 parameters. This one already highlighted to you. This is the SSP power in general, total power for the SSP power. This can be got from the SEP1 or R0 configuration in a standalone. And this indicates what is the power of a single resource element used by the broadcast and the SSS. And the one which I was speaking about, it's called power control offset, which is usually, if you zoom in here, you'll find it usually under the CSI measurement configuration resources. You'll find something called here, I didn't highlight it, but it's here, power control offset, as you can see. For example, here it's 0. There is no offset. There is no offset. And what this one do, if you again go back to the explanation, this one specifies the transmit power differences between CSI and the rest BDCH. And the main idea that whenever you increase the CRS, this means you will have a less power in the BDSH, because you will borrow from the BDSH channels. So this means you might have a less CQI. But again, this is depend on the scenarios. Sometimes it might give an impact, sometimes it might give a negative impact. So it depends on the scenario. The other one, which I didn't see it, I even was expecting to find it within the same message, but I didn't. It's called power control offset to the SSS. And this is specified the transmit power differences between CSRS and the synchrogen signal. and also higher value for that CSRS. This means you have a less SRS power, and this might impact your access as well. And that's it for today's video. I hope if you like the video, just share it and press like and comment. And see you next video. Thank you very much.